So today I'm going to discuss our recent work on the coupling of the effects of protostellar outflows, feedback, radiation feedback, magnetic fields, turbulence, on the formation of massive stars and also massive clusters. And I'm going to discuss the physics associated, the relative importance of the physics associated with all of these processes as we go through the different stages of star formation. Now, constructing any theory, predictive theory of star formation in and of itself a grand challenge problem. And we're dealing with a large range of physical processes involving gravity, supersonic turbulence, hydrodynamics, outflows, two flavors of radiation, both ionizing and direct radiation, and non-ionizing, magnetic fields, two flavors of magnetic fields, ideal and non-ideal in chemistry. But the complexity is that these are highly coupled nonlinear feedback mechanisms existing among these processes, and they have to actually be calculated fairly accurately across an extremely large dynamic range in both time and spatial scales of the problem. If you consider for a moment that the giant molecular clouds, which are the birthplaces of star formation, are themselves tens of parsecs in a linear scale, and they have a gathering scale for the mass to produce them that's on the order of or larger than the galactic atomic radius, which is on the order of 200 parsecs up to a kiloparsec in the interstellar medium, with young clusters that have separations on the order of about 10 to the minus 2 parsecs, down to stars that are 10 to the minus 7 parsecs. You have to basically solve this collection of physics, highly coupled across 9 orders of magnitude and length scale. The dense regions that form these clusters themselves are embedded within the giant molecular clouds, and the clouds themselves are embedded on the higher scale in the galactic disk. But the problem is that these larger environments, which contribute significant inputs to the lower scales on both mass, kinetic energy, and confining pressure, are needed crucially to provide us with realistic initial conditions on the smaller scales, but almost no simulations use this information because you have to compute at that scale to get it, and so they use highly idealized initial conditions. Furthermore, and we've heard quite a bit about this yesterday, our simulations, because of the length and time involved, have really only explored a very small phase of parameter space. So to get to exascale, and clearly this is an exascale-worthy grand challenge, we have to have fundamental changes in both the algorithms and the code architecture to even use an exascale architecture. Let me start with a recent simulation, a paper we're about to publish with Pak-Shing Lee, where we start at several parsecs. This is a highly magnetized, supersonically magnetized cloud, and this is showing the collapse of that cloud about 800,000 years after it begins its collapse. It's in fact an infrared dark cloud, which is a birthplace for high mass star formation, and it produces giant filaments on the order of several parsecs in length. The global magnetic field is along the z-axis here, and this structure ranges over 4 to 5 or so orders of magnitude in density. The streamlines, if we blow up a small region here, the streamlines of the magnetic field thread the filament and are perpendicular to its filamentary structure. Crucially, in that filament, we can start to see the formation of cores, and these cores are the embryos in which stars form. So if we take that filament, and we basically, hello, I'm supposed to get a nice, okay. If we take that filament and we rotate it, so we can see the structure of it, and these filaments are now observed, and they're braided structures, and we have great correspondence to what's actually seen. We see the development of these embryos of stars within the filaments, and I'm going to concentrate on a high-density core, because that high-density core has to further collapse to produce an actual high-mass star. So let's actually concentrate in on that region there. Okay, if we do that, we basically will then see the complexity of the collapse of that object as it produces a central high-mass star, 25 solar masses in mass, gives forth very violent bipolar outflows. In addition to that feedback, we have feedback from the radiation itself, all interacting with filaments that are trying to accrete mass to build this star, and yet we have these feedback mechanisms that make the entire environment around the object itself entirely complex. So this is the type of complexity that we have to overcome as we go further down in scale. Now, if we go further down in scale from this and go to a resolution of about 1 AU, we now see the emergence of a Keplerian disk. We have to see a disk because the disk eventually fragments to give us a smaller system of stars and eventually planetary systems. This disk cannot be seen at resolutions that are typical. You have to go down to about 1 AU to get the disk. What's significant about this is that magnetic fields have been thought for a long time to be so efficient in their magnetic braking that you can't form a disk. But it now turns out that with supersonic turbulence presence, this breaks the strong efficiency of magnetic braking, and disks can actually form. And that's a whole other topic, but the formation mechanism of these disks is still an open question about how the turbulence does this. In the simulations that I've just shown you, the dynamic range from turbulent clouds down to cores, down to the disks, is about 6 orders of magnitude. This means that with a fixed grid, you're dealing with a problem that would require 10 to the 18 effective cells. You can't touch this problem without adaptive mesh refinement. Okay, now, there are several outstanding challenges that face us in the massive star formation and cluster formation. We're going to investigate the physics that comes into play at each stage in forming this. So the first is, how do these feedback mechanisms, which couple protostellar outflows with radiation heating and couple to magnetic fields, affect cluster formation? And inevitably, how do they affect the initial mass function? Furthermore, an outstanding question, which we believe we've now solved, is how can gravitationally collapsing clouds overcome the so-called Eddington barrier that, due to radiation pressure, would prevent the formation of a high-mass star? And we believe that we've shown now how that problem gets itself solved through a combination of Rayleigh-Taylor instabilities and outflows during the formation process. To attack these problems over the last several years at Berkeley, we built Orion. It is a full 3D adaptive mesh refinement magneto-radiation hydrodynamic code. Currently lives in a Chombo AMR framework. It has self-gravity, sync particles, stellar evolutionary models, second-order Godunov schemes, multi-grid solves, protostellar outflows, and parallel adaptive ray trace ionization. That's the direct ionization. The radiation transport, which is crucial due to dust reprocessed radiation, comes in 2 flavors, gray and also multi-group flux-limited diffusion. We have formulated this in a mixed-frame formulation so that we are correct to order V over C in the static diffusion regime and to leading order in the dynamic diffusion regime and the free streaming regime. And I want to point out that all of these regimes in this highly coupled system of parabolic elliptic equations are basically encountered during the star formation process. Our MHD is a very robust Godunov dimensionally unsplit corner transport upwind method, and it has constrained transport, which guarantees to machine accuracy the constraint of dB equals 0. This permits us to get to the very high supersonically Mach turbulent flows in a very stable fashion. Now, the outstanding challenges of cluster formation bring with it outstanding challenges for the IMF. The IMF is most easily measured in young clusters, and it's observed to be invariant in both its shape and its characteristic scale in the clusters and also in the field. Theories that describe the properties based on an isothermal gas on turbulent fragmentation or competitive accretion can predict the shape for the IMF, but an isothermal gas, as we've shown in 2010, does not have a characteristic mass scale. As a result, standard turbulent fragmentation based on an isothermal picture can't determine the location of the IMF peak. So it has to appeal either to additional physics, which I'll discuss, or define some fiducial cloud in which the properties of that cloud are picked to determine the IMF peak. But the problem with that is it's not clear on what scale you pick these properties. So this then points to us to say that the IMF peak and its invariance cannot be found in the physics of an isothermal gas. You have to have departures from isothermality and the nature of turbulent fragmentation must then be made with a fully consistent solution of the gas dynamics for any theory that seeks to explain the characteristic mass scale. Okay, then you get down to the core scale. The core scale is crucial in how it fragments. The question of how magnetic cores fragment is extremely important for any theory in star formation in which the IMF is set in the gas phase. Now, previous attempts to do this are limited pictures. In one attempt by Peters et al., they include the magnetic field and direct radiation, but they neglect the all-important dust reprocess radiation, and that's the radiation that's crucial for regulating how the fragmentation process works. Krumholz et al. Included dust process radiation, but they don't have subgrid scale models, so their simulations were forced to halt at only a very tiny fraction of the core collapse, so they can't study fragmentation of the bulk of the gas. Now, observations of the core mass function tell us that there's a very strong correspondence between that and the IMF. In fact, it looks like a scaled up version of the IMF. The correspondence of the core mass function being essentially the same as the IMF, but shifted up in mass by a few, can be naturally explained if the massive cores themselves don't fragment strongly, and they end up, in fact, with most, about a third of their mass going into a single mass star or a very low number of accompanying stars, and I'll show exactly how that works. So let's start with the equations of radiation hydrodynamics. So these are the familiar equations, except for the right-hand side, which I'll talk about for a few minutes. These are the equations of mass conservation, of mass, momentum, and energy, coupled on the right-hand side, coupling the matter field to the radiation field. These equations themselves must be coupled to the next higher moments of the radiation field. This is the radiation energy equation and the radiation momentum equation. And these quantities, these energies, these moments of the energy, the flux, and the radiation pressure tensor are integrals, double integrals, excuse me, over the angle and frequency of the intensity of the radiation field. And that right-hand side that couples the matter field to the radiative field is in fact a 4-force density. It is a tensor in the laboratory frame of the fluid, and it is directly related and equal, except for a reverse in sign, to the radiation energy stress tensor. What those quantities are basically breaks the components of that tensor are a time-like component, which is in fact the energy absorption from the radiation field minus the energy emission for the fluid, and the space-like component, which has three subcomponents, is the rate of the momentum absorption from the radiation field minus the rate of momentum emission. And you can derive precisely, relativistically correct, that 4-force density to all orders of V over C. So without going through all the algebra, you get this type of a mess. You can begin to simplify that by expanding that in powers of beta. What's crucial here is that you keep this consistent to order V over C. This means that you have to retain terms in the expansion to order beta squared. When you do that, you simplify those terms to a certain degree, and then again going through a lot of algebra and term ordering, you end up with the complete set of mixed frame equations of graviton, radiation, magnetohydrodynamics to order V over C. And this is actually a scaled down version of what we have in Orion. It's a more general set that we have in Orion. But these equations must all be solved in a coupled manner, and they are an elliptic parabolic set of equations that basically retain accuracy to V over C in all the crucial regimes of star formation. Now let me start at the mass scale of the cluster, and I'm going to build the physics up to show you the relative importance of physics as it comes into play as we go through the different scales of star formation. Here we're looking at a massive cluster which for the first time included radiative feedback, but had the turbulence just put on the initial velocity, but essentially a smooth density and no outflow feedback in this simulation. As the cloud is actually evolving, we see a network of filaments forming. The cores form within the filaments, collapse and form stars. The stars radiatively put their feedback into the entire cluster. And in this case, and we weren't prepared for this, it overheats the entire cluster. It's too efficient in its radiative feedback. So let's see what I mean by that. If we follow the evolution of what I've just told you, the radiative feedback has a dramatic effect on the evolution of a massive cluster. Once about 20% of the mass of that cluster is processed into stars, the radiative feedback halts further fragmentation. But accretion continues. This means that stars that already exist continue to increase their mass, and this moves the initial mass function into a higher mass, so it becomes increasingly top-heavy, and it's inconsistent with the IMF. We see that at about 6/10 of a free fall time, we already have distinct regions of the feedback around these stars in the gas of the cluster. But at 90% of a free fall time, these regions have overlapped and the entire cluster becomes heated, which tells us that we need more physics because the global collapse scenario is not compatible with the stellar IMF. It is too top heavy. So now let's look at that in a little more detail. Let's compare the differential mass distribution of stars and clusters that we get with a Chabrier observed IMF, and that's the calculations are in different resolutions in red and blue here. As I go increasingly in time downward, let's look at this last panel. And basically the grayscale here is a Chabrier IMF at the 10th and 90% percentile level. We note that when we get to 50% of the mass in the cluster having been converted to stars, the mass in almost every bin above between 1 and 10 solar masses is already above 90 percentile in random draws from the Chabrier IMF. So the central problem is that the median mass increases continuously in time due to a radiative suppression, an over-radiative suppression of fragmentation, and this overheating is a new phenomenon in cluster formation. Now, you don't see this in simulations of low mass, low density clusters. And what we've shown is that those regions of heating are locally confined around the stars, but if you go to high mass clusters, the stars are basically clustered in denser regions, their accretion rates are higher, and so all the gas in the cluster becomes heated. So now you have to bring in the next level of physics. The next level of physics is that the turbulence has to be completely self-consistent. You need outflow feedback and magnetic fields. All of these things will basically obtain a lower star formation rate, and that will presumably bring the problem back into where it should be in comparing with the observed IMF. So basically, if we look at what I've just shown you, here's the time dependence of that computed IMF as it reaches the Chabrier IMF, overshoots it and, on the high end, undershoots it on the low end, and so we have a top-heavy IMF in late time. So now we go to the next level of simulation.
What happens if you continue to run it? Is it possible that it oscillates around and eventually relaxes?
No, we've looked at that. The point is it's overshotted. It doesn't go in the other direction. You continue to build mass in the stars that already exist. Okay, now the next level of physics has to come in. You now need feedback due to protostellar outflows, okay? And you need a self-consistent turbulence in the initial velocity and the density, and you need to drive this at the larger scales. And driving it at the larger scales is crucial because that's where the turbulent cascade comes from. The turbulence now decays on a longer time scale for smaller isolated clouds, and so the turbulence can have more of an effect in upholding this too efficient formation of stars. So let's see how that works. As this cloud begins to evolve with all this feedback in it, we start to again have radiative feedback, but now the radiative feedback has much less of an effect in heating the overall cluster. And so we can study the cluster star formation history with full turbulence, radiation, and protostellar outflow feedback, all self-consistent. And let's just concentrate on this top graph here. Here I'm showing the fractional total mass in stars as a function of freefall time. The star formation in the so-called smooth turbulent run without outflows undergoes an exponential increase as time approaches asymptotically a freefall time, while the star formation in turbulent runs that are fully self-consistent turbulence and with outflows, that's the red line, drop dramatically in the acceleration of star formation. So we see here that if you calculate the dimensionless star formation rate in these turbulent runs is still on the order of about 0.3, and it's still an order of magnitude too high to nail observations. But it's already an order of magnitude lower than without all the feedback that we've had in this simulation. So turbulence becomes a significant mechanism now for regulating star formation without magnetic fields. I'll get to magnetic fields in a few moments. The outflows actually further lower the star formation rate by about 20%, but the outflows are somewhat less important feedback mechanism at this stage than regulating the star formation than turbulence. Okay, now if I recompute the cumulative mass function, or the stellar IMF, with this amount of full feedback in the problem, and we compare this with what we've just seen, we can now see the effect of the feedback. Now, the turbulent wind case stays statistically consistent in time with an observed IMF at most times, while we hit the IMF top heavy without all that feedback, and we we get an underrepresentation of the IMF at the low end side. As I said, the star formation rate is still too high. Outflows here account for 20% of the star formation rate. Now, let's go to, we're about to publish this paper. It's the first simulation of the evolution of a massive cluster that has turbulence, protostellar outflows, magnetic fields, and radiation feedback all coupled. These recent simulations that we've done with our graduate student, Andrew Myers, who's just about to finish up, we've looked at these clusters. These cluster calculations take on the order of 1 to 2 million hours per cluster, running on anywhere from 500 to 2,048 cores. Sustained runs take 2 to 3, 4 months at a time. These calculations show what happens as we go from clusters that have mass to flux ratios of 10, and this is in fact at the tail end of what's being observed, to clusters that have stronger magnetic fields that basically have mass to flux ratios of about 2. That is typical for what observers actually see, and the corresponding plasma betas are 0.24 and 10 to the minus 1. You notice that one of the first major effects in this cluster formation of the magnetic fields is that they tend to drive the stars into smaller area regions and higher density regions with much more evacuated space where no star formation occurs. And the reason for that is that to get an overall mass to flux ratio of 2, which is moderate, you have to have subregions that are subcritical and therefore can't form stars. So most of the stars, in fact, go to these regions that are supercritical, and they're confined to these much smaller surface areas. Now, we can study the cluster star formation history here, and I won't bore you with the details, but we've done very detailed convergence studies on this, very rigorous, and we've determined that at 46 AU, you are highly converged in this problem, but actually most of the simulations where I'll do analysis and talk about it are 23 AU. We note that there's a monotonic increase. Here I'm looking at the star formation efficiency. Here I'm looking at the number of stars formed. A monotonic decrease in both the star formation efficiency and the number of stars at a given time with the field strength. And we study now the reduction of that star formation efficiency going from the case with no magnetic fields, that's mu5 infinity, all the way down to the strong field case. And we find that reduction in star formation efficiency and number of stars is around 2. And oddly enough, this is very similar to what Patrick Henneville got 2 years ago without having the crucial physics of radiative feedback. I believe his calculations were isothermal, and he started with a spherical object. The star formation efficiencies here follow a very similar pattern of relatively slow star formation initially, in which the star formation rate then increases with time, followed by a period with roughly constant rate of star formation. And to compute the dimensionless star formation rate, because that's what we're going to compare with observations, we basically compute the slope at a particular point, and we now find that the star formation rate with full feedback is coming right in line, very close to what observers actually see, just a few % efficiency. No magnetic fields, that efficiency would jump back up to an order of magnitude higher to about 0.12. So now, let's look at the IMF. This is not just hydro, this is the complete radiation hydro case with outflows and no magnetic fields, and the weak field case with outflows, magnetic fields, radiative feedback, everything else, and the strong field case. We're looking at the differential mass distribution for clusters at a time when the mass is gathered in stars is about 20 solar masses. We find that the distributions are extremely well fit by log normal distributions. The strong field case here is, okay, so the histograms are the data from the actual simulation, going from no magnetic field all the way up to strong magnetic field. The solid lines are basically the log normal distribution fits, and the dotted lines are log normal distribution fits to a Chabrier IMF. And we see that as we move toward what observers actually see, mass to flux ratios of about 2, we're now starting to come in line with full physics, with the Chabrier IMF, but we still have a characteristic mass that's lower than about 40%. And the reason for that is that these were very, very lengthy calculations. We didn't continue them all the way. Many of the stars are only recently formed, and some of them, or most of them, are still accreting mass from the surroundings. So as this simulation is continued on in time, the expectation is that we will now, with full-fledged physics, start to reproduce the IMF. The strong field case is more in agreement with the Chabrier IMF than either the no field case or the weak field case. Now let me go further down into the turbulent core to show you what actually happens in the formation of a high mass star. So we're going down in scale. These were the first simulations of high mass star formation with turbulence, radiation feedback, protostellar outflows feedback, and magnetic fields and sync particles. So now I'm looking at individual cores. We just published this work 3 months ago with Andrew, and I want to point out 3 cases here. I want to isolate the importance of radiation and magnetic fields separately and coupled nonlinearly. On the case on the left, I'm looking at hydrodynamics with radiative transfer and outflows. There is no magnetic field. Here I'm looking at MHD in the isothermal approximation, no radiation, and now I'm looking at the coupling of the two. What you're going to see is that simulations of the turbulent cores that have either the magnetic field or the radiation alone will result in a formation of a multiple low mass star formation in a single high mass star. So let's actually look at that. First, without the magnetic fields, there's a lot of evolution that took place. I'm showing a point. You can't really see it because this is orders of magnitude in where the high mass stars form. And you'll note that we get a cluster of low mass stars accompanying it. And these filaments are relatively thin and they collapse efficiently to form these cores that go to stars. If I now go to the case without radiation and just look at the effects of the magnetic field, both of these cases suppress low mass star formation, but not enough. We again end up with a low mass cluster and a high mass star. It is only when you have magnetic fields non-linearly interacting with the radiation feedback that you can fully suppress multiple star formation, which leave you with a high mass star and a single low mass star. And that's the final simulation here. If I can get the hand out of the way. You'll see that even the filamentary structure here is dramatically different. These are very fat filaments because both the magnetic field and the radiation are providing feedback to keep those filaments from actually collapsing. And you end up, in fact, with a high mass star and a low mass companion. So typical massive cores here, which are centrally condensed and have the observed mass to flux ratio for the magnetic field, do not fragment strongly. And this is what you get to basically explain the core mass and IMF correspondence.
Are you using sync particles?
Yes, yeah.
And do you have the ability for sync particles to merge?
Yes.
So they, in the case where you have the clusters, they don't merge?
That is correct. We have a mechanism for sync particle merger if objects are less than 0.05, and that's really your first collapse phase of a star. Anything above that retains itself as a star. Okay, now how do we understand this? How is it that a molecular cloud core that has a mass of hundreds of solar masses puts most of its mass into a single massive star rather than fragmenting into hundreds of solar masses? And to get at how this happens, you have to look at the thermodynamics of the situation. So here I'm looking at thermodynamic phase plots in density and temperature, and the colors represent the mass in a density temperature bin. As I look at, let's say, the middle case, it's maybe hard for you to read, which is the MHD case without radiation, we see that the magnetic field raises the temperature, okay, this is temperature, this is density, raises the temperature in low density gas, but thereby suppressing fragmentation in that dilute gas, which is far from the central object that's giving the radiation feedback. On the other hand, if I look at radiation feedback alone without magnetic fields, I see that this raises the effective temperature in the high-density gas, the gas that's basically close to the star itself, and it suppresses fragmentation there. It is only when magnetic fields and radiation act together that you can suppress the fragmentation effectively in one more than either region alone, because now you're covering the entire domain in which these two important processes can suppress fragmentation. So in fact, if you look again at this middle column, and this is the last time snapshot of the middle column, this has far more gas, okay, cold gas, and at high density. And that's exactly the regime where you would form low mass stars. When you incorporate the radiative feedback into the simulations, this gas isn't even present. And this means that the radiation interacting with the magnetic field gives you essentially no gas in that region, and so the low mass star formation is very efficiently suppressed, and you get essentially a single high mass star. Now, there are severe limitations in these types of calculations, and a major obstacle of scaling these high dynamic range radiation hydrodynamic calculations is the relatively poor parallel performance by using the standard model of domain decomposition. And this is especially exacerbated with adaptive mesh refinement. With adaptive mesh refinement, the parallelism is typically achieved by running one MPI process per core, and then we distribute the grids on every level over the MPI tasks and use algorithms that give us a load balancing. But strategy is very efficient, and we've shown this to achieve weak scaling, which for highly idealized problems, because when people tell you how they've scaled to hundreds of thousands of processors, you take a careful look at what the problem is. They're typically very idealized. You achieve good scaling out to about 32,000 cores. However, weak scaling is basically irrelevant for high dynamic range problems in star formation because the computational cost is dominated by the highest resolved regions, where the Courant time, which is really what dictates your time step, is smallest, and the total number of resolution elements is often modest. So let's consider the following. These simulations of massive clusters take at least 1 million CPU hours. Yet at the highest level of refinement, where you really care, they only have about 20 million cells. Why is this small? It's small because the volume filling factor of these high density regions is usually and typically small in self-gravitating systems. So you have large regions where there's no action. This represents now a fundamental problem for a straightforward domain decomposition parallelism, because if you spread 20 million cells over your 32,000 cores, you get grids that are on the order of about 8 cubed. But even the simplest schemes that you would use, where AMR would require at least a single ghost zone, and in fact, usually several. Even for a single ghost zone, that 8 cube grid has as many ghost cells as real cells. For 3 ghost zones, the cells outnumber the real ones by more than a factor of 4. And in fact, we use 4 ghost zones. It goes up from there. So you get a cripplingly high cost in the communication and redundant computations. So you have to get around this. The major difficulty is generic for any system where a relatively small volume evolves on a rapid time scale compared to the bulk of the computational domain, but the feedback is occurring from that small region, and yet it dynamically affects the entire domain everywhere. That's the problem of star formation. For realistic multiple scale multi-physics problems, as opposed to weak scaling studies, none of the existing high dynamic range codes with coupled physics scale well to more than a few thousand cores, and this is the reason. So you have to combine MPI domain composition over the nodes, at least with a threaded share memory approach within nodes. If you do that, then rerunning those numbers, 20 million cells running on 32,000 cores, handled by, of order 2,000 MPI processes, each corresponding to a 16-core node running 16 threads, you now get domains that are considerably larger in size naturally. The ghost-to-cell ratio here is only a fraction of what it was, even when you, and it goes up to about 1 when you use 3 ghost zones, but it's now small enough to avoid the unreasonable communication costs. So a hybrid approach to parallelism is at least a start to provide better strong scaling than current MPI-only codes for star formation, and this may be crucial for exascale. So now I want to talk about improvement in the physics that would use this hybrid approach. Hybrid methods address problems that where both point sources and reprocessed radiation are both crucial for star formation feedback. Using moment approaches alone, as I've described today, severely limits the angular resolution of the radiation field in the vicinity of the point sources. So what we're doing right now is bringing in a long characteristic approach coupled with the moment approach to give us the additional high angular accuracy coming from the direct radiation. So the way you can do that is to automatically generate OpenMP threaded code equivalent to the original do loops where the grids are still parallelized over MPI. But now one runs one MPI task per node, and within that task updates on single grids, which are parallelized over OpenMP. Then you've got to deal with the implicit solves. This is a bit of a more difficult problem, because you have implicit solves. You have highly non-local operators with radiative transfer, something you don't have in just ray trace. So you have to thread the linear solves for the implicit updates in the FLD. Now, we get these solves via calls to Hyper. Hyper provides an OpenMP support, and code interfaces with Hyper can be modified. And this can, in the end, result in a coupled FLD. The next step is also to thread the long characteristics. Here, you're faced with a different problem. The LC long characteristics contain outer loops over the rays, all rays that pass through a grid. And the inner loop traces each ray over the cells as it encounters that grid. So the rays on a single grid are independent of each other. So the outer loop becomes the natural place to insert the OpenMP directives, but the operation is a serial operation. The subtlety here in threading the outer loop is load balancing. And the reason it is because not all these characteristic segments pass through a single ray and are of equal length. In fact, by definition, they're not. So you have to, they don't require the same amount of work to ray trace. So what you have to do is basically distribute those rays in custom blocks, and that will lead to a fully threaded LC. Okay, so let me, do I have like 1 minute or something like this?
You're up to 36 minutes now.
Okay, I'll just quickly go over the summary and then get to the challenges in less than a minute. We've shown that for the formation of massive stars, magnetic fields and radiation feedback are crucial for the suppression of multiple star formation, leaving a single massive star. We show how the correspondence between the core mass function, the IMAF, and the IMF actually has an actual explanation. A point to note is that radiation outflow, radiation feedback and outflow feedback do not prevent the formation of high mass stars, but we also don't have a natural limit. Yet, the formation of massive clusters, we've shown that the standard global scenario is incompatible with an observed IMF, but if you have now the appropriate physics in and the turbulent driving and internal mechanical feedback from protostellar outflows, you can then show that you get an IMF that for the first time is shown to be invariant and in excellent agreement with the IMF for various kinds of IMFs. Okay. We've got the first published work that actually reproduces that IMF in a cluster like the Orion Nebula that is large enough to contain massive stars where the peak of the mass function now is determined by a fully self-consistent solution of the gas thermodynamics. And the first mass clusters to date that include all these effects. Now, what are the challenges? Well, number one, major challenge, self-consistent initial conditions obtained from the outer scale, as I pointed out at the beginning of the talk. That needs to be incorporated into the simulations. So we're not inventing initial conditions on these lower scales. The next advance in radiation transport, in my opinion, is the full development of a threaded variable Eddington tensor approach that goes beyond what I described to you, long characteristics with moments. We need to get resolutions down to the radius of the star itself. And we need to do this to be able to generate self-generated magnetocentrifugally driven protostellar outflows. And that's where you start dealing with the total dynamic range of a factor of 1 billion. And the solutions, these types of solutions can then provide far more accurate subgrid scale models back up to the higher scales of galaxy formation. And as I said yesterday, an approach to this would be to have those simulations being improved by our supplying far more accurate subgrid scale models in which they then can redo their simulations and improve our initial conditions at the outer scale. And with that, I'll end.